So we're going to talk about network communities, and we're going to define them in a second. But the first idea is, like, if you look at this graph, you probably realize that there are some groups of nodes that are more tightly connected among themselves than with the rest of the graph. So what I mean is, look at this, right? There are a bunch of nodes that are very, very, very tightly coupled among themselves, meaning there's like lots of connections in there, right? Something is happening here. They're like pretty dense area of the graph. Maybe this one, they're all connected to the same node. Something here is happening. So there are regions where there are sort of more connections locally, right, than in general in the graph. Can you see that? Yeah. All right. So we're going to talk about network communities. We're going to define them. Another name for network communities would be cluster of nodes. Again, the cluster of nodes will be those type of nodes that are well connected, and I would say connected more among themselves than with the rest of the graph. And so what makes a community, right? We're going to try to come up with certain definitions. It's not very easy, but we're still going to do this. What I outlined here, it actually comes from the famous book by Westermann and Faust on social network analysis. And the way they define a community or cohesive subgroup, it's through the following properties. So pretty much, everyone in the group has ties to one another and to majority of nodes within the group. The groups are always very often compact, which means the nodes within the group are either directly connected or maybe connected in a small number of steps, so maybe in one node. But still there is very, very small distance from any node within the cluster to any other node in the cluster. If you look at the edges, you realize that the density of the edges, like local density within the group, is typically much higher than the density in general in the graph. So it's high frequency of ties within the group relative to overall frequency of ties within the graph. And so if I go back to this picture, what we're saying is, yes, so within the community, you'll get nodes very often connected directly or maybe in one step, and overall density of the edges is higher in those areas, right, in those communities, than in general within the graph. And overall speaking of communities, you kind of intuitively understand that if there is a group of people, for example, here, and some of you know each other, but you don't know everyone, right? You can actually probably by looking at you guys find some groups that know each other much better, right? Maybe you're from the same program or from the same department, and you know other people less. And so if you look at this friendship or acquaintances as a graph, you'll have those small groups, communities that know each other much better than the rest. And so if I try to plot the picture, it will look like higher density and closer connections. Okay? So we can actually, if we'll start looking at the graphs, we can think about communities of two types. One we will call non-overlapping community, and non-overlapping community is a situation when every node belongs to its own community. And so right here on the left-hand side, we can think about these guys as being one community, there's another community, and there's another community. And so notice that every node in this case belongs only to one community, to one group of nodes. Situation on the right-hand side is slightly different. If you notice, there is this node D that belongs to both communities, right? If you think about, again, tightly coupled groups of people, these guys are all well connected, and these guys are all well connected. And there is this node D that you can put it into this community, but then it's sort of, you'll cut it from those guys, which feels like he also can belong to, right? And so this is a situation which is called overlapping communities, which is when there are a couple communities and they intersect over some node or maybe several members, right? So in social networks, you usually can have both of the situations. In this lecture, we're going to focus on this type of community detection. So the goal for us today would be to learn algorithms that will allow us to detect those communities. So by looking at the graph and analyzing graph, being able to find out groups of nodes that are more tightly connected among themselves than with the rest of the graph. And so we're going to go for non-overlapping community, which means for every node, we'll say it belongs to this community, either belongs to community A, community B, community C. We're not going to look at the situation where the node can belong to two communities. Now, those algorithms also exist. They're slightly different. We're not going to focus on them right now. Okay. So I'm going to try to define the community through the following statement. So network communities are groups of vertices that the vertices inside the group connected with many more edges among them than with the rest of the group. This is somewhat vague definition, right, and not typical for mathematical formulation, but that's sort of what people used to, and that's we're going to deal with it. And the reason for this somewhat vague definition is because we could force within the definition, we could try to say that, look, we will call community on only those group of nodes where every node connected to every other node within the group. We can do that. But that's going to be a very, very rare occasion when that actually happens. And so if we do that, we'll have very, very few communities. And so we would like to kind of have a little bit more relaxed definition. And so it's actually very hard to give you a precise definition in terms of like mathematical terms. And so what people usually do is they say, okay, look, by looking at this picture, it's sort of obvious that there should be three communities here, right? Three groups of nodes. And it's a group of vertices and nodes such that inside the group, they have connection or connected by many more edges than between the groups, right? So by literally, eyeballing this, you can actually see those communities. And the question is if we can come up with algorithms that allows us to find those three communities, okay? Split the graph into those three communities. Any questions so far? Does it make sense? Okay. So just following this type of definition, what can we, how can we put some mathematics behind this definition so that we can, come up with algorithms that will help us to find those communities? Well, the first thing you can think of is this density notion, right? As I said, if you look overall on the density of edges and the density of edges within each of the community, you'll have more edges within the community than on the average within the graph. And so what you can try to do is you can define densities. And the density, graph density is defined by number of edges that are present in the graph, divided by the maximum possible number of edges that you could have in the graph. So if there is n nodes in the graph, then n times n minus 1, that's how many, divided by 2, that's how many pairs are there. And if each pair of the nodes in the graph connected, that graph is completely dense. Density would be 1. And if it's not, well, that's sort of the graph density. Then we can actually use the same definition, but to calculate internal density for the community. So what we can do is we can say, look, let's count only those edges that are inside the community and only those nodes that are part of the community. So looking at this, if I want to do density for this community, I will count 1, 2, 3, 4, 5 nodes. So the maximum number of edges there, if there are 5 nodes, is 5 times 4, 20 divided by 2, 10. And then I count 1, 2, 3, 4, 5, 6, 7, 8 edges here. So the density is 0.8 for that particular community. I can also calculate external edges, counting number of external edges for the community. And the same way here is going to be 1, 2, 3, and you divide by the same, normalized by the same number. And you can compare those type of densities. And if internal density, for example, is greater than external or much greater than the density or overall density in the graph, that's sort of your community, right? and the denser it is, the better. Now, that actually gives you some numerical value that can help you to characterize a community. The challenge is, though, I can easily calculate that number when I already have communities. I can actually just then count all those nodes that are in communities and edges. But the challenge is, if you don't have any assignment or you don't have communities, how do you actually detect them? So it's one of those things where the problem of when you have communities, calculate the values is easy. What's hard is to actually find the communities. All right, so that's one metric we can do, density. There are actually other metrics you can do, and there are some other metrics that are a little bit more practical in terms of building algorithms upon them. So the idea is the following. We can actually calculate, to determine the communities, we can calculate how many edges we can remove from the graph to separate that community from the rest of the graph. And that way we can define a community. So let me for a second go back here. In this picture, in order to separate, for example, this community from the rest of the graph, how many edges do I need to cut or remove? 4, right? 1, 2, 3, 4, and that's going to be removed. To separate this guy, how many edges? 3, right? So, but if I want to, for example, cut through, like split this guy, say going right here, I'll have to cut 1, 2, 3, 4, 5, 6, 7 edges, right? So if I cut 7 edges, I'll split this in 2. But that's not a good split. But if I cut only 4 edges here, that might be a pretty good split. So I can actually convert this problem of finding communities into the problem of finding those edges I need to remove, right? So in some sense, again, if I try to bring this analogy of, I don't know, of road maps, and again, think about St. Petersburg, and the road and the squares are nodes, right, and the roads connecting them, that what I'm trying to say is, in order to split this into communities or sort of regions that have more roads connecting them than with the rest of the city, I'll probably need to find bridges, right? If I find bridges, I remove them, that will split city into very natural groups, right? And so in some sense, you can think about those are bridges, right? So if I can find those bridges, then I can do this graph partitioning, and then I can actually detect communities. So there are metrics to do this. The simplest metric is actually graph cut. And graph cut, it is just literally the number of edges you need to cut to separate the community, to separate the subgraph. So in this case, let's say if this is one community, which I know is community, then I will need, this would be my cut, so I'll have to cut all these edges. I'm not saying this is a small number, but I need to cut all these edges, and I'll just count. And so the cut here would be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so in order to cut out this group of nodes, right, it will cost me 17 cuts to do this. Okay? Now, you can think of, okay, well, maybe this is not a good group of nodes. Maybe, I can cut them right here. Instead of cutting these edges, I will kind of take these nodes and think about them as being part of outside world and my cluster being, just what's internally. So I'll have to cut, fewer edges here. That's also a cut, and we'll need to compare them. Sometimes cut, can be a good metric, sometimes not very good metric, because if I just count the cut, which is the number of edges I need to remove to cut out piece of the graph, I don't take into account how many nodes will be within that piece that I remove. In some sense, I mean, if I look at this guy, right, I can do this cut, remove only 2 edges, which is very cheap, And I can say, oh, well, this is a community. Right? So cut by itself, yeah, it can be metric, but if I just blindly apply it and look for the cheapest cut, right, because that's sort of the most obvious solution, I might end up like removing, one node. And so what you typically do, you would think of computing not just cut, but some other metric, which would be, for example, the cut divided by, the number of, for example, of nodes that you cut out, right? And then you look at that relative metric. So in this case, for example, if I do it this way, what was it, like 17, 18, then I have to divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, divided by, say, 14 nodes, right? Or by the number of edges that remains inside there. That's another option. So in any case, what I'm trying to do is I'm trying to see somehow the amount of edges I need to remove to split, to separate the graph in pieces versus how many nodes or edges will remain within each piece to make sure I don't cut out like little tiny small pieces. That's the idea. And also that's sort of a metric I can use, right? If it's small, I do a good job. Yet there is one more metric which is quite popular. It's called modularity. So the idea is the following. When you look at the graph, let me bring this graph, or we can look at this graph, and we look at the edges. The edges, internal and external. Sometimes it's actually hard to say if that's sort of a lot of edges or not, right? Because to say that there is that this is quite dense, there's a lot of edges, you need to be able to compare against something. And so the idea of this modularity metric is the following. You compare the number of edges within the clusters to the number of edges that would exist if this graph was completely random. So the same size, the same number of edges, but they're like randomly connecting nodes. And what you do is you're just kind of comparing it against that number. And then you say, okay, if I get in some region of the graph, if I have more edges than the graph would have there if it was random, and it wouldn't have any clusters at all, so if I have more, then I do have some clusters in there.
This randomness is like by Erdős-Rényi model or something like this?
You can do this. Yeah, you can use Erdős-Rényi with the same number of nodes and same number of edges, but just randomly connecting it. And imagine if it is randomly connected, you probably will not see, those guys, but then you kind of subtract one from another, and the difference will show you those areas where you have denser number of edges. And you do this because it's hard to, otherwise, you need something to compare against, and that gives you this option. Now, in practice, of course, you do not generate that random graph. You can actually use mathematical properties to see what it would look like. And so this formula, in fact, just tells you look, there is this modularity metric which compares the number of edges within the community versus how many edges would be there if that was a random graph. And the modularity score is again counting number of edges within the community divided by the total number of edges in the graph minus this strange number, but this number is actually theoretically you can show that if the graph was random, that how many edges it would be there. So it is one of the metrics. It's sort of the most, it's not the easiest metric, right, compared to the previous two. It's not obvious, but actually this works pretty well. And let me just give you an example on this metric. Now, the score for this metric is kind of interesting. Here's an example. That strange modularity metric has a score 0 if you put all the nodes in one community. If you do really strange assignment, and what's here is every color is its own community, right? What I did here, I said, okay, this is one community, this is another community, this is a third community, this is one more community, another community. So I'll just did that every node its own community. That modularity score will be very negative. I mean, it will be negative, so not good. If I can do this type of assignment, right, where I would say, okay, all the purple nodes are one community and the green nodes are another community, that would be the modularity score. And finally, if I do sort of the best job of assigning nodes to communities, and I say, okay, well, this is a guy's one community, these guys are in another community, then the score will be the largest. Okay? So, the point being, the score reflects how well you assign nodes to community. And when your assignment to community is good, right, matches the actual community thing, then the score will be pretty high. When you have suboptimal assignment, it will be lower. When you have like crazy assignment, it will be very low. So what you can do is when you do this community detection or assigning every node to its own community, you can actually calculate that number, that modularity score, and based on that, you can either say that your assignment is good, or you can just use the score directly to go through different possible partitions until you find a good community structure. Let me pause here for a second and ask if this makes sense, what we're trying to do. So again, community detection is about finding natural groups of nodes. Right? As I said, there could be different ways to defining them, but we do know that in communities, within a community, nodes are more tightly connected among themselves than in between the communities. We could think about this partitioning problem as, for example, removing the edge in between communities, if we can find that edge or the few edges to remove. Or we can think about any other way of assigning nodes to communities, but we need to have some sort of metric that will tell us if our assignment is good. And here, this is a perfect assignment because it's very natural, one community, another community. And when this assignment happens, when you assign all these nodes to one community, all these nodes to another community, there is this modularity metric that becomes maximal. And if your assignment is a little worse, well, the metric is smaller. And so in some sense, you can build an algorithm that tries different assignments of nodes to communities, trying to maximize that metric. Any questions? Yes?
Why is the scores are different on one graph?
Oh, they're different because, okay, the way they calculate it is I go over, so this is a modularity score. I go over all possible communities. I count number of edges internal to those communities divided by the total number of edges in the graph, and I use those metrics, sum of node degrees within the community. So what's shown here is different communities, different assignments. Here I would say when it's purple, I'm saying my community is this, and the second community is this. All right? So that's the way I decided to split this. If I do it, what I need to do is there's these two communities, and within each of them, I need to calculate this ratio and that number. So here, for this community, there's 1, 2, 3 edges internal to it. So this is going to be 3 for one community, and for another one, there'll be 1, 2, 3, 4, 5, 6, 7 internal edges, right? So this is going to be 3 over, and total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, wait a minute, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, over 13, right? So it's going to be 3 over 13 plus, what was it, 7? 2, 3, 4, 5, over 13, right? Those are the numbers. Okay? That's when I calculated for this graph, for this assignment. Now, here we have the same graph, but very different assignment. Here I believe this is one community, this is another community. I calculate the same type of numbers, but now it's going to be 1, 2, 3, 4, 5, 6, 7 within one community, right? And there's going to be a 1, 2, 3, 4, 1, 2, 3, 4, 5 within another community, right? And so that's, I compute those ratios plus I compute that number, okay? And when you do that, for the community distribution here, for the assignment, the total number, the total score will be 0, 2, 2, and here it's going to be 0, 4, 1. Does it make sense, what we computed here? Okay, and what I'm saying is this intended to show you that when you have a correct assignment, because obviously the community structure here is these guys and these guys, the score is larger. Yes?
So is this aimed at deriving where are the edges of two communities, right? Is it used for deriving edges of
You mean this?
more than two communities? Yeah.
Can we have more than two communities? Yes, we can have more than two communities. Yeah, we can have 5 communities, 10 communities. We have as many as we want. And in terms of, is that what you're asking?
Yeah, I thought that we've been comparing to. Could you please turn back?
Sure.
Yeah.
So what happens again, this is the ratio of number of nodes, edges within the community over total number of edges, and this is sum of node degrees within the community divided by total number of edges. Now, this part comes from this random graph situation, right? This is what we currently have in your graph. And so what I'm saying is you're comparing the relative number of edges that you have minus you're reflecting it against the number of edges that would be there if the graph was random. And there is, I don't want to go into details, but this actually tells you how many, with this number of nodes, would be in their edges if the graph was random.
So we need to have an initial understanding of how many communities should be inside the domain.
That's a good question. Okay, look. Right now, what I'm showing you is when you have your community, how to evaluate it, right? We're not yet we're not yet talking about the algorithm how to get the community, right? So it's again, one step further, we're going to do this. But right now, what I'm saying is, if your algorithm, whatever algorithm, give you this as a community detection, right? Saying that this is one community and this is another community, you can actually evaluate the quality of this detection using this modularity score, and it will give you this number. Now, if you take your communities from the algorithm, and it will give you this as a one community, that's as another community, you can calculate the modularity score, and it's going to be higher, and that gives you a metric to compare the quality, because clearly this is a better community detection than this. Make some sense? No? Yes? Yeah. Okay. All right. So, pretty much to sum up what I just described. So we have a optimization criterion. So we know that we can either look at the density, we can look at this graph cut, which is the number of edges we need to remove. We can use this modularity score we just looked at the previous slide to see if what we have is a good community. But we also need to have a method to actually, finding those good communities. And in fact, what happens is that, you can think about exactly solving this, which means let's go and try all the possible partitions, right? What I mean is let's go and say, okay, this is community 1, and the rest is another. This is community of one node, and the rest is a second community, right? This is a community of one node, and the rest is. Then we can pick up 2 nodes as a community, 3 nodes, etc., right? So you can try to do this. Unfortunately, it's factorially large number of combinations you need to go over, and so you just cannot do it unless the graph is extremely small. So for this, you could possibly do it, but if you have thousands of nodes, there is no way to do it. And that's called NP-hard problem. It's just because there is just too many combinations. In fact, if you, for example, want to do this bipartition, like I'm showing in the previous graph, which is just splitting into 2 parts, right? Splitting graph into 2 pieces, then there is that many combinations possible, which is n factorial divided by n1 factorial and 2 factorial, where n1 and n2 are different sizes, even if I have fixed sizes. So there is no exact solution, there is only approximate solutions, and they can be done through what's called greedy algorithms or various heuristic algorithms. So what I'm trying to tell you guys is the problem is very, very challenging because on one hand, at the beginning, we don't have a very precise definition of the community, right? And so we're basing it off our understanding that community in general should have more edges internally than externally, right? On the other hand, even if we come up with good metrics for this community, then it's still challenging to actually find the optimum in terms of those metrics because there's just too many options, right? It's just factorially large. Now, how many of you guys had a class in, I don't know, in data mining or in machine learning, and some sort of advanced analytics? Remember clustering problems, right? Clustering when you have a group of nodes, group of points, and you're trying to find you have points and you're trying to find some groups of those points that are closer to each other than with the rest of the points, right? That is the same type of a problem. It's pretty much, clustering of nodes on the graph. So, what do we do? Well, there are a bunch of algorithms that people came up with. One important point is you cannot, some of the algorithms are based a little bit more on, on the better mathematics. Others are based on on sort of heuristics. Ultimate check is you run those algorithms and verify how well they work, right? And even then, it's also quite challenging to compare algorithms because there are so many different metrics by which you can compare. You can compare by the density of those clusters. You can compare by the modularity score. You can compare by number of edges you need to remove from the graph. So there are very many metrics you can use. And so typically when people look at this graph partitioning, they try to, different algorithms, and then they compare results and based on different metrics, and they try to see, if in one metric the algorithm is much better than others, and then they use that. But again, this kind of compared to some other problems, this is not a very well defined problem, and there is no sort of, absolute correct answer. The same way as with clustering. There are better clustering, some clusterings are better than others, but there is no sort of the right clustering because it's unsupervised. You don't know what the right clustering is. Now, one last comment before we go into actual algorithms is the following. When you look at those at this communities, or whatever we call them, there are a couple ways of detecting them. And it's also kind of with clustering. One way is you can say, look, I'm going to just try to detect right away all the communities that that I'm looking for. I might even up front decide that I want to split the graph into 5 communities. The same way as k-means clustering, right? You just say, I want that many clusters. And then you can, instantly cut them out. If the graph is good and if there's that many clusters. If you try to cut out more clusters than naturally in the graph, well, you'll get sort of not so good communities. Another approach, which is very popular, is divide and conquer approach, or recursive partitioning, where you can take a graph, you can split it into pieces, right? By, for example, removing those edges or some other way. And then you take each of the pieces and start working on each of them independently. Let's, for example, here split it. And you keep doing it until you reach kind of dense groups of nodes. And then those will be communities. Okay? So, either way is doable. In practice, people more often use this, recursive partitioning when you divide it every time into 2. Okay? So let's talk about a couple of algorithms. Again, as I mentioned, there was like lots and lots of algorithms doing very different things. Some of them are very strictly mathematically based. Some of them are a little bit more sort of heuristics. I just picked up two of the algorithms that are, one is easier to understand, the other one is actually probably the best today and the most popular today. So the first one is called edge betweenness. And the idea is the following. Again, to understand this algorithm, think about, imagine stay in Pittsburgh. You want to sort of split it into parts. Think about bridges and think about traffic. So where would you expect to have traffic jams? Right? On the bridges, because that's where all the traffic, the one that wants to cross the city, will go through. Remember, last time we talked about centrality metrics for nodes. Which metric was about shortest path? Speak up. Betweenness centrality, right? There was like we talked about closeness centrality, we talked about degree centrality, we talked about betweenness centrality. And so betweenness centrality was defined through the number of shortest path, overall number of different shortest path from different nodes to different other nodes in the graph that go through a particular node. So the same way we can actually define the edge betweenness, which is, we're just looking again at the shortest path between different pairs of nodes in the graph, but instead of looking at how many of them goes through a particular node, we just see how many of them go through a particular edge. And so imagine that you have this graph, and you pick up pairs of nodes in this graph, and then you calculate shortest path, and you calculate shortest path through all possible pairs of nodes. Then for every edge, there will be some number of shortest path that go through that edge, right? And if you look at this picture, which edges do you think will have the most number of shortest path that will go through them? Most likely these edges, right? Those that are bridges. Because if you want to get from any node here to any node there, you have to go through those three edges. There's no other way, right? Any node from here to any node there, you have to go through those two edges. So the idea of the algorithm is the following. Very, very simple idea. You calculate all the shortest path that can go through the graph, and for every edge, you compute all the number of shortest paths that go through this edge, right? And then you pick up those edge that has the largest number of shortest paths that go through it, which is sort of the bridge, right? The main bridge, if you wish, and you remove it. Traffic will redistribute, right? The number of shortest paths that go through other bridges will change. You rank them again, and you remove the one that has the largest number of shortest path going through it. And you just keep doing it until your graph splits into two pieces. And then you pick each of them and just repeat this exercise. And by doing so, you will eventually get to the point where you see those separate clusters. And so that's the algorithm. So it's called edge betweenness because that's exactly what it does, right? Computes, uses edge betweenness proposed by Newman and Girvin in 2004. And so what you do is, again, for each edge, compute edge betweenness, sort them, and remove edge with the largest edge betweenness. And just keep doing it and going and going and going through this exercise. And you stop when graph splits into two components, right? And that allows you to split graph into two pieces. Then you can pick up each piece and repeat this exercise on that piece of the graph. Make sense? Can you do that? If I ask you to code it, can you code it? All right. Well, the good news again, you don't need to code it. There is a function in R that does it for you, right? As a result, you will get this. It's called Dendogram, which is the way things split into pieces, right? There is first split when you remove one edge, the graph splits into two pieces, and then you just keep going until the graph kind of splits into more and more communities. And there are some obvious communities here, which is 1, 2, 3. But if you keep going with this approach, you will actually notice that this can be split into two communities, this can be split into two communities, this can be split into two communities also, right? The question is when to stop splitting them. It's a good question. We're going to look in a second at the metric that allows us to stop. But here's an example with a karate club, right? With the same graph we keep looking at for a long time. And again, if you remember, I think I told you the story, right, about this graph in the very first lecture, that this was a karate club, like actual karate club, where sociologists were testing some hypothesis with their students. And so what happened is the club split into two, and some students went with one instructor and other students remained with other instructor. And so the researchers knew what the ground truth is, right? So when the club split, they knew who came with whom. And so then they say, okay, look, can we predict the split based on the structure of the network? Can we predict the split based on the connectivity pattern? And so that's sort of why this graph also became popular. So we take this graph, we run this algorithm, and this is a split into two communities that the algorithm finds for us. So based on the structure, if you calculate, you take this guy and you take those guys and calculate, say, the number of edges internally, and then compare it to how many connects them. It might not be very obvious here, but the algorithm picks up those two as two communities. Now, having said that, I told you that with the algorithm, we can actually keep splitting, right? We can say, okay, well, we split into two. Let's just put this into algorithm again and see if it splits more. And in fact, it does. If you put it and keep splitting, it will say, well, there is these guys that are kind of well connected, and etc. To see when to stop, we can use, for example, the modularity metric, the one we just discussed previously, to see if the proposed division into communities matches the structure well, right? Remember how we calculated it. Where is it? Right here. So now it's an algorithm that gives us those partitions, and we can calculate that number, right? And so what happens if we start computing that, it actually shows us that modularity grows approximately to, I think, 1, 2, 3, 4, 5 clusters, and then it starts dropping. And so, which means, according to all the theory, that that probably here the optimal number of clusters is actually, based on the structure, would be 5. So if it's split into 5 pieces, that would be the optimal, sort of, from the point of view of the modularity split. You had a question.
Yeah. For one number of clusters, we can have many different partitions.
Yeah.
And what's the point on the plot? It's the best score.
Say it again, for the same number of clusters might have, yes. Yeah, so this is okay. What this does is a number of, so this gives us not just a random partition, this gives us a partition that is created by Betweenness, by edge Betweenness algorithm. So edge Betweenness algorithm created for us a partition, right? The only thing that we do not know in this case is if we have two of those. So in terms of splitting this graph into two pieces, we believe that this is the best the algorithm does for us, right? Now there is no questions in terms of, if the boundary should be somewhere else. It found for us the boundary. Now the question we have that remains: should we continue, and should we split this into 3 clusters, right? And if we keep doing, it's going to be 3 clusters. Now again, splitting into 3 clusters, according to this algorithm, this is the best way to split it into 3, according to this algorithm, right? So the question is, should we stop at 3 or should we continue cutting it? And the answer to this is this modularity score. And so for this particular split, for the split provided by this algorithm, it gives you the best one, this, which is, I think, probably 5 clusters, right? Now, I intentionally emphasize that based on this algorithm, right? So this particular splits, this particular partitioning is done by this algorithm. If you run some other algorithm, it might give you slightly different clusters, right? And then, if you're a good scientist, you'll probably go through this modularity calculation again and select out of those algorithms which works best on this graph, right? But if we stay within the algorithm, that's as good as it gets within this algorithm. Make sense? Any other questions, guys? This is sort of, I'm trying not to go deep into the theory, and actually I'm completely skipping this theory of how this works. I'm trying to make it quite practical, right? So you can actually run the algorithm. So if you just take this graph and give it to this edge betweenness, it will actually ask you, it might ask you like when to stop, right? I think it will ask you like how many iterations to do or how many partitions to give. And the answer to that is you can go through those and then you can calculate modularity score for each of those partitions, and the one that has the largest one, that's the best for this. And so that's, for example, this edge betweenness gives the highest modularity score, and I was lying for 6 clusters. So according to that algorithm and the modularity score, the optimal partitioning within that graph is 6 clusters. Now, do I see it in terms of, the picture I'm looking at? Well, I don't know. Maybe it's not a perfect layout. So for me, it's actually more convincing. This is sort of a little bit more convincing that this is the optimal partitioning. But again, that's sort of the metric we're using. With respect to the metric, with respect to the algorithm, that's the best we can do. Okay? So again, compared to many other things, this graph partitioning the same way as a clustering problem. There is no unique sort of correct solution, right? You're trying different solutions, you're trying different metrics, you get, you stop on what you feel the best. And you feel the best meaning, what's the best for the metric you're using. Right? Okay. Let's move on. I'm going to go over one more algorithm, which is in fact, now the problem with the previous algorithm, edge betweenness, it's kind of understandable, right? So you can easily imagine how it works, removing edge after edge after edge. The challenge there is you have to keep recomputing shortest paths to do that, right? Because the algorithm is based on all the shortest path. And computing shortest path is expensive. And so if you have a lot of nodes, it is actually computationally difficult to do, right? And so that algorithm works all right, well on smaller graphs. It has problems working on the larger graphs. And so in order to work on larger graphs, there are other algorithms. And one of them, in fact, this is the most popular, this algorithm, sometimes it's called Blondel by its last name of the guy. Sometimes it's called Alluvion Method because it's Alluvion University where he was a postdoc. We're going to talk about this algorithm again. I'm going to sort of wave my hands through this so you'll know a little bit what's happening inside so you can use it. So this algorithm is actually explicitly looking at this formula. So remember, on the previous algorithm that we discussed, the algorithm would look at the edge betweenness, right? And then, calculate things, and eventually we would look at the modularity score. This one looks and computes and optimizes the score from the very beginning. So it just explicitly optimizes this. It's multi-level, so it's hierarchical scheme. And it's heuristic, which means there is no good math behind this, why it works. In a sense, it optimizes the good function, but the way it does is every time, on every step, trying to make it bigger and bigger and bigger, but in what's called greedy manner, which is it just every time, every step it maximizes it. It doesn't look like further away what's going to happen in 5 steps and 10 steps. It just says, okay, on this step, if I do this, I increase this function. If I increase it, I do it. Right? So the way it works, and this is an example how it actually works, this clustering, the detection of clusters or communities. And it's shown on the size, 2 million phones, 2 million mobile phone network. And this is a call graph where every node is a mobile phone on mobile number, and every edge is a call. And in fact, that's done in some of the European countries. And it's color-coded based, in fact, it's kind of funny, it's color-coded based on the languages spoken in those countries. I think it's about, I think it was, Germany and France, and then there is, on an intersection, there is another country where people speak both German and French, right? I think it's Belgium, Germany, and France or something. Anyway, so that's sort of the algorithm run, just to show you like large numbers. So what does the algorithm do? I'm gonna again, guys, hand wave through this. I'll just give you some ideas so you will kind of get the feel of the algorithm. Don't worry if you don't understand in depth what's actually happening there, but you'll get some notion. So it actually starts with all the nodes, and every node in this algorithm on the very first step belongs to its own community. So here, 15 nodes, so 15 communities, right? Every node considered as its own community. And then what you start doing is you pick up a node. Let's say you start with this first node or 0 node, and you say, okay, look, if I take this and I merge it with this guy and I calculate that modularity score, will it get better or not? Right? So does the algorithm believe that this is a better thing to join them? I calculate that number, I remember it. I calculate joining this and this, merging them into one cluster. Merging this guy and this neighbor to one cluster, merging this guy and this neighbor to one cluster. So I pretty much can take this guy and merge either with this, with this, with this, or with this. And I just choose which one I'm going to merge with. And I will merge it with the node where after merging, this modularity score of the graph will improve. Okay? Because the higher the modularity score, the more your clustering, or the more your community represents the structure of the graph. So I do it. I merge it with one of those guys. Then I go and pick up the second node number 1, and repeat this exercise and merge with somebody else. Go number 2, repeat this exercise, etc., etc., etc. So I'm going to go through this type of exercise for every node, again, starting with every node being its own cluster. And after I go through this exercise for this particular graph, what's going to happen is only 3, well, actually 4 types of clusters remains. There will be these guys sort of merging into one, these guys, and these guys. And then what I'm going to do is I'm going to say, okay, look, I think this is one cluster, this is another cluster, this is another cluster, this is another cluster, or community. Let me group them in what I call super node into one big fat node. Group these guys into one fat node, group these guys into one node, group these guys into one node. I'll keep all the edges in between them. And then I repeat this exercise. I will try to merge this guy with this or with this, see which works better, merge them, and keep going until eventually I'll get 2 communities, right? And based on that, going through this process, I'll have this hierarchical structure of communities, and then I can look back and stop at any time. And if I feel like I need to have 4 communities, I'll stop here. If I need to have 2 communities, I stop here, etc., etc., right? Make some sense? Yes? No? Previous story, we started from the top of the graph. We looked for the edge that has we looked for the edges, right, that have the highest betweenness, and we remove them and keep splitting the things. Here, we go sort of other way around. We pick up nodes and start merging them into groups. And the difference is over there, we looked at this betweenness metric. Here, we kind of monitor that modularity score right away. and we do the merging, that gives us the biggest improvement to this modularity score, largest marginal improvements to the modularity score. And we could just keep doing it. And then we get, then we get our graph partitioning. So if I run this algorithm fast community unfolding on the graph, on this karate graph, this is the optimal structure. And notice what's interesting. This one says the best possible partition is 4 clusters, and that's the modularity score. Now, let me go back to the best result from this guy. For this guy, the best modularity score was 6 clusters and this number. So which of those 2 algorithms works better on this graph? The second one, right? So, and pretty much that's how you deal with these algorithms. You take your graph, you run the algorithm, you see what it gives you in terms of like, okay, with 2 clusters, 3 clusters, for each of them you calculate the modularity score, you look at it and say, okay, well, that's modularity score. Then you pick up a different algorithm and run it. And you see, oh, look, here is actually this one believes that there are 4 clusters. That's the optimal number of clusters. But guess what? It actually showed much better modularity score. So that actually worked better. And if you look at this, I think to me this makes more sense, right? This partitioning. Again, just from eyeballing. Not all graphs you can actually look at them because some graphs are much, very large. But in this one, this makes sense. So, bottom line, various algorithms, there exist various algorithms, there exist various metrics that allows you to check on this quality of the partitioning. I would recommend looking at the modularity score as a quality of the partitioning. And in terms of algorithm, this last one, the Alluvion method, is probably, works the best. So if you take just out of the box and you want to detect communities, I would recommend using that. And this is also the result of this Alluvion method on, some very large artificial graph, but quite complicated. And so it just shows you, if you go hierarchically, how it actually detects various levels of communities, right? So it's actually very, very, very powerful. So that's pretty much it. I just wanted to show you this slide. This is, I think, 2010. And back then, there was at least that many algorithms, quite known algorithms in community detection, right, with different authors and different algorithm complexity. Again, this is like 2010. So since then, there has been more work. It's probably, for right now, there are probably many more algorithms that are well known. This algorithm we just described is probably still the best in terms of the performance and overall quality. But some algorithms just sort of better for a particular application, works better for particular applications than others. It is very hard to say which algorithm will work better for which network. And so, in some sense, this community detection problem is, experimental problem. You pick up your graph, you take a few algorithms, and within the R package, there are a bunch of those. You run your graph through those algorithms. You calculate modularity score for the partitioning you compare them, you pick up the best. So that's sort of the overall algorithm of how you do community detection these days. And as always, there's like a bunch of references if you're interested in them. All right, any questions?